Okay, so let's look at a code to do exactly what I just showed you on the whiteboard and run some tests to gain a little bit more intuition about what we mean by all this funniness. Okay, so I have this code, I put it in the Dropbox, and this is going to literally create these matrices, these B by U matrices. And I think the example I gave, B was 3, so let's just do that, and U is 4. So B is M equals 2 to the B buckets, right? And recall that the size of the universe, S equals, we tend to call U equals 2 to the U, okay? So in other words, in this particular example, although we can do any size we want, we have 16 possible keys in the universe, numbers 0 to 15, and we have 8 buckets in our underlying hash table, and we want to make a statement about the probability of conflict between pairs of keys, or again, if you take one key and hash it against and hash all the other keys, what are the chances of a conflict? How many conflicts are you going to get with that key? Okay, those are the two claims. So that's my B and U that I showed you in the lecture. So for example, a random B by U matrix might look like this. If you remember, the one in the lecture looks a little bit different, but there are 2 to the 12th of these things. And we're going to create all of them, and we're going to find out for how many of them any two particular keys conflict. And that is really our probabilistic statement. And so I think that's the sort of clearest way to see it. So let's just look at it. There's a little bit of sort of pushing bits around in the program, but the idea is simple. Hopefully I commented it. And that is the number of distinct matrices is going to be 2 to the B times U. So there are 2 to the 12th. That's important to realize. There are 2 to the 12th different ones of these. Okay, so those are the H's, little h's, in our universal family, big H. There are 2 to the 12th little h's. So we want to look at all 2 to the 12th of them, right? Because that's going to give meaning to the idea of a probability of a hash conflict. So there are n distinct matrices. I'm going to count how many conflicts there are when we go through all of them and try to hash 2 different keys, right? So this is my data structure to store one of these H's. So H is of size B by U, and I'm going to keep filling it until I fill it with all 2 of the 12 possibilities. Yeah, this stores the bit pattern of the int that I am hashing as a key, just as an array of bits, just for convenience, okay? And HX and HU are my hash values of my keys, and they're arrays of size U, right? Because, let's see if I did that right. Maybe it should be, it doesn't have to be size U, it could be size. Okay, so I fixed that. The keys that are hashed are only need to be of size B. They don't need to be of size U. But the input keys are of size U, right? So, wait. Yeah, that's right. Okay. Because you're squeezing 4-bit keys into a 3-bit table. Okay. So let's do this. Let's take 2 arbitrary keys. And this is the statement that's made in the theorem. So we're going to take 2 arbitrary keys, 1, 0, 0, 0. Can be absolutely anything. And we could loop over all keys. Let's put a couple ones here. Just, I don't know, so you don't get uncomfortable with all the zeros. All right, so we're going to take 2 arbitrary keys. Then we're going to, for each possible matrix, we're going to look at the effect of hashing the key, each key with the matrix. So I'm going to create the next matrix, and I just assume I have a function that does this. It creates all 2 to the 12th of those. And then I'm going to, so that don't worry about that. These are just debugging things to demonstrate that I've done it right. Then I'm going to hash each key with new H in H, right? And then what I'm going to do is I'm going to see if they hash to the same key, so, or to the same value. So do hashes conflict? And so what is the statement? Okay, well, the statement is if I examined all little h and capital H, that 1 over capital M of them, in this case, 1/8 of them, would conflict, right? So if I explore all these, and there are 2 to the 12th of these possible different little h's, then that would mean that 2 to the 9th should conflict. Not two, if there, sorry, if there were 2 to the 12th different matrices, there's a factor of 2 fewer keys or bins in the hash table, so 2 to the 11th. So 1 out of 8 would be, you'd expect 2 to the 11th come. Is that right? No, let me think about it for a second. Hold on. Something's confusing me a little bit. Okay, I resolved the issue. I was changing the code one place, but I was in a different directory running an old version that was never changed. So it started to scramble my intuition. So I said it right the first time, which is that there are 1 over 2 to the b, or 1/8 of the randomly chosen hash functions will produce a conflict. Okay, so if there are 2 to the 12th different hash functions, which is I think 4096, then there should be 2 to the 9th different of 2 to the 9th of them should cause a conflict if the theorem is accurate. Okay, so if we compile this, not sure, I did not get that error ever before when I was compiling this. So let me see if I have another version issue still. Oh, let's just see if it runs. Okay, let me see what happened there. Okay, I accidentally added a spurious token in the program when I was editing it, so now it works. There was never any issue, is the final word of all of this. So if I run this, I get 512 conflicts, and 512 is 2 times 4, 8, 7, 30, 512, 2 to the 9th power. Okay, so let's just review what that means one more time. That means that of the 4,096 different little h's from capital H, 512 of them produced a conflict between these two keys. And the theorem says that it has to be the case for any two keys. I just picked 2 at random where the keys are different. So if I recompile it, I should get 512 no matter what I do, but no matter which 2 keys I do. And I'm looping over all the matrices. So there's nothing really to change there. So I could have a double loop over all keys and all matrices, but I'd rather just sort of persuade you by doing a few different pairs of keys. And so the computer's has some memory issue right now, but I'll just ignore it. So I get 512. Okay, so the only other thing maybe we could do is just sort of change the change the size of the keys will make it so this will take a while to run, because now we're going to have 2 to the 8. Maybe that's still small enough. We're going to have 2 to the 18th different matrices to explore. Okay, and again, only 1 over m, or 1/8 of those matrices, is going to cause a conflict, but now that's going to be 2 to the 18th minus 3, just 2 to the 15th. So it's going to be a much larger number. So we should see 2 to the 15th conflicts. So we'll make the table bigger. That's the last little thing we'll do. Okay, so now we have 2 to the 15th conflicts. Okay, and let's make, this is the way that you do well. You say, all right, we'll make the table bigger, and we get a factor of 2 fewer conflicts. That's going to take a little while to run. Not quite sure what happened there. Let me take a look at that. Okay, that number is exactly right, because maybe I didn't think about it right, but there are 2 to the 24th now different little h's and big H, and 2 to the 4th of them are, the guarantee is that 1 out of every 16 of them are going to conflict. So 2 to the 24th times 2 to the minus 4 is 2 to the 20th, and 2 to the 20th is the number that we saw of conflicts. Okay, so you, it appears as we poke around with different keys that this property is holding. So this is actually quite clever and quite interesting and a really good illustration. But let's just remember the main point of what it means. It means if you randomly choose one of these hash functions, little h, from this family, in this case of 2 to the 24, 8 different possibilities, that there is a 1 out of 16 chance that you're going to have a conflict for any particular pair of numbers. Okay, and that's true for all pairs. So for any pair of keys, once you pick a little h, the chance that that pair of keys conflicts is 1 out of 16. And that statement is true for every pair of keys that you can compare out of the universe of keys, capital U. Okay, so that does not necessarily say anything about what is going to happen when you pull out a little hash function. I mean, a specific hash function, little h, out of big H. You could want to hash 2 keys, and those 2 keys could hash the same location. But it says what happens in expectation. So it's that last step that I want to make meaningful, and I'll do that in the last segment.